Hey everyone, and welcome to This Explainer. Today, we are dissecting a true marvel of mechanical engineering, the drilling machine. Whether you're an engineering student just stepping into a manufacturing lab for the first time, or maybe an enthusiast who really wants a deeper understanding of workshop machinery, you are in the exact right place. We are going to break down this absolutely vital machine piece by piece.
All right, let's jump right in. Now, if you're used to doing a few home repairs here and there, you're probably pretty familiar with your standard handheld power drill, right? But when we move into industrial or serious workshop settings, that handheld drill just isn't going to cut it. We need a drill press, or a stationary drilling machine. This is the ultimate tool for exact, repetitive, and most importantly, safe hole making. See, with a handheld drill, human error can easily give you a crooked hole. But a drill press is a fixed, motorized machine that practically guarantees your drill bit goes exactly where you want it at the perfect angle every single time.
Before we start picking apart the individual pieces, let's just take a second to appreciate the big picture. From the heavy base planted firmly on the floor all the way up to the motor and drive system sitting at the very top, this is a beautiful system where every single component relies on the next. It's like a giant puzzle, and if you don't understand how these parts operate together, you'll have a really hard time troubleshooting if something goes wrong.
To keep things simple and avoid getting overwhelmed, we're going to organize this machine kind of like human anatomy. We'll start with foundation and support, then move into powering the rotation, check out the cutting mechanics, explore precision and control, and finally, bring it all together in the complete system.
Starting right at the bottom with Section 1, Foundation and Support, essentially the skeleton of the machine.
Building from the ground up, we have the base. This is your heavy anchor. It's made of solid steel or iron and is basically there to absorb all the vibration. In fact, it's usually bolted directly to the floor. Rising straight out of that base is the column. This rugged, cylindrical pillar is the vertical backbone keeping everything perfectly aligned. Honestly, the accuracy of your work relies entirely on the stiffness of this column. And finally, we have the table. Think of this as your adjustable stage. It rides up and down the column to fit your material. What's crucial here is that it sits at exactly 90 degrees to the drill bit though. On a lot of models, you can actually tilt it for angled drilling too.
Moving on to Section 2, Powering the Rotation, the heart and muscles of the operation.
Now that we've got our skeleton, we need some muscle. The flow of power here is fascinating. First, the electric motor, usually tucked away on the upper back, generates the primary rotational power. This motor drives a belt and pulley system. And here's the cool part. By physically moving the V-belts on those stepped pulleys, you actually change the gear ratio, which controls how fast the machine spins. Finally, all that kinetic energy is transferred down into the spindle, a high-carbon steel shaft that carries the power straight to the tool.
Now, here's a mechanical distinction that trips up a lot of beginners, so pay close attention. We have the spindle and we have the quill. The spindle is the inner shaft that actually spins, but the spindle is housed completely inside the quill. The quill itself does not rotate, it's just an outer sleeve. When you pull the handle on a drill press, you're actually moving the quill up and down. So the quill plunges vertically, carrying that rapidly spinning spindle right down into your workpiece. Make sense?
All right, on to Section 3, the cutting mechanics, the hands of the operation.
Down at the business end of the spindle, we have the chuck, essentially the gripping hand of the machine. You'll mostly run into two styles here. Keyed chucks use a geared key to physically lock down the internal jaws. They provide maximum gripping torque, which is absolutely critical for heavy-duty machining where a slipping bit would be a disaster. On the flip side, we have keyless chucks. These have a self-tightening collar that actually grips harder as the machine applies torque. They're total game changers for fast-paced shops where you're swapping out bits by hand all day long.
And clamped tightly inside that chuck is, of course, the drill bit itself. This is the star of the show. As the spindle spins, the sharp fluted edges of the drill bit are forced into the material, literally shaving and shearing away solid metal or wood, leaving you with a perfectly round, exact hole.
Which brings us to Section 4, Precision and Control. The brain of the machine.
Because let's face it, raw power is totally useless without control. Sitting way up at the top of the column is the head, this heavy metal casting that houses all the upper components. Front and center is your on-off switch, placed right there for immediate emergency access. Off to the side, we've got the feed handle. This uses a rack and pinion gear system that lets you smoothly plunge the quill downward with just your arm strength. Right next to that is the depth stop. This is a brilliant little adjustable collar that physically stops the quill from traveling past a certain point, guaranteeing you get identical hole depths every single time you pull the lever.
Okay, we absolutely have to talk about the unsung hero, and arguably the most critical safety feature here, the workpiece clamp, or vise. Listen,
You must lock your material down. If you just hold a piece of metal with your bare hand and that drill bit catches, the rotational force is going to instantly rip that metal right out of your grip. It's literally called a helicoptering workpiece, and trust me, it spins violently. It can cause severe injuries and easily snap your drill bit right in half. A high-quality vise holds the material perfectly flat against the table, absorbing all those forces so you stay safe.
Also, if you're looking at larger industrial-grade setups, like big radial drilling machines, you're going to see a built-in coolant or lubrication system. Drilling through thick, solid steel generates a ridiculous amount of heat and friction. These systems constantly flood the cutting zone with fluid, usually mostly water mixed with specialized coolants to dissipate that extreme heat. It saves your drill bits from burning up and leaves a way cleaner finish on the metal.
And finally, Section 5, the complete system. Machine anatomy in perfect unison.
We've zoomed way in on all these microcomponents, so let's zoom back out. When you unite a sturdy, vibration-free foundation, dynamic power flowing from the motor through the pulleys, sharp mechanics locked tightly in the chuck, and precise controls like the feed handle and depth stop, all 15 of these parts function as one unified system. You set your speed, clamp your work down firmly, hit the power, and smoothly pull the lever. The result? Absolute mechanical perfection.
This basic anatomy really is the foundation of all modern machining. But it leaves us with a pretty fascinating question to ponder. This exact tried-and-true setup has driven manufacturing for over a century. But today, as these tools evolve into heavily automated computer-driven CNC systems that practically run themselves, what fundamental human skills do you think will remain irreplaceable on the shop floor of the future? Because knowing the anatomy of the machine is really just step one. Actually mastering it, well, that's an art. Thanks so much for joining me on this explainer, and I'll catch you next time.